Hello folks, we're going to get started now. Any latecomers will just have to come in late. I'm Daniel Berrange.
I'm Thomas Huth.
We're going to talk to you about the next generation QEMU functional testing framework that you've probably seen being developed over the past year or so. Everything in this presentation has been written by humans, apart from the silly emu pictures that you'll see. So to start off with a bit of history about the QEMU testing situation, there's quite a variety of test suites in QEMU. There's unit tests, there's the I/O tests, TCG tests, Q tests, and they're all kind of slightly different from each other. But we didn't really have end-to-end testing of real virtual machine workloads until relatively recently. When we did the functional testing, we wanted to be able to write tests more easily than some of the unit tests or Q tests. So Python was an obvious choice of language, along with helpers for dealing with disk image assets and other files that the tests might need. So the original functional testing framework, we got help from the maintainers of the Avocado project. And they developed the first QEMU functional test suite, provided the test harness and the basic infrastructure. This was initially called acceptance tests, but then later got renamed to Avocado tests. Now, the Avocado testing system was a great start, but there were some difficulties we had with Avocado over the years. It's quite a complicated system to deal with. Especially when the average QEMU developer is more of a C maintainer, not so familiar with Python, and Avocado was a relatively complicated Python program at that, which just added to the difficulty. The other unfortunate thing was that after the initial contribution of the Avocado testing suite, the Avocado maintainers didn't really do much proactive help when we were trying to debug problems with failing tests or understand what was going on with the test suite and so on. This was a particular problem when we tried to upgrade the version of Avocado that was in use with QEMU. So we got stuck on quite an old version, version 88, which was from 2021. So that's 4 years old, and Avocado kept on moving on. We tried to upgrade Avocado, but kept on hitting stumbling blocks with the newer versions, causing regressions for us. And this all really came to a head last year when the version of Avocado we were using turned out to be incompatible with new Python. So we needed to find a solution to that problem. So Thomas already started this, having a bit of a reconsideration of what functional testing meant in the context of QEMU in 2024. If we look back to 2018, there were lots of different test harnesses. Each different QEMU test suite had its own harness for running tests. But by 2024, QEMU had converted to use meson as its build system, and most of the test suites had also converted to use meson as the test runner, which simplified things. So at this point, Avocado was a bit of an oddball, as Avocado was still a test runner, as well as providing the test infrastructure APIs. And having the Avocado test runner in between the tests and meson just further complicated the debugging when things went wrong. Then in about 2022, Annie contributed the BIOS bits test suite, and he initially did this as a standalone Python test. And we convinced him to port it over to Avocado because we didn't want to introduce a new test framework. But in retrospect, Annie was going down the right avenue with his attempt to provide a standalone Python test runner. So Thomas basically had the idea that we could take the Avocado tests and port them over to a new standalone Python test runner framework.
So right, to see whether we could port the Avocado tests with a reasonable amount of work to another standalone framework, let's have a look at one of the Avocado tests first. So this is an example for a typical Avocado-based test. As you can see, there's something like a basic test class, the QEMU system test class. And the good thing is that this test class is part of the QEMU repository. So this is not part of Avocado itself. It's a class that we have in a QEMU repository. So by adapting that test class to become independent from Avocado, we could tackle already a lot of problems. That test class is doing just the basic stuff like managing the VMs, as you can see at the end of the test, like adding parameters to QEMU, launching the VM, and handling console input and output of the guest. Then there's something like a timeout setting, so that is used by the test runner to cancel the test after a couple of seconds if in case the test is stuck. And you can see here a subtest method. So the functions that start with the test underscore prefix, these are the subtests. So each file can have multiple subtests, and they are run independently. Then there's something like a decorator, which can be used to skip the test in case a condition is not met. And there are tags. Tags serve two purposes in the Avocado framework, at least in the one that we use in QEMU. First one is the obvious one. You can use the tags to only run a subset of the available tests by specifying a tag on a command line. And the second one was that Avocado used these tags to configure the QEMU machine and the QEMU binary automatically. Then there's some code for handling asset downloading. So this code fetches a file from the internet, checks the hash sum, and extracts it so that the test can use the files in that archive. So that's basically what we needed to come up with a list of things we had to tackle. I don't want to go into details here. We will do that in the next slides. Just maybe a short word about the tags. So we don't have a replacement for selecting tests with tags yet in a new framework, simply because the Meson test runner does not support tags. There are some ideas floating around how that could be replaced, but so far it's not such an important feature, so we didn't tackle that yet. Of course, we have a replacement for the second meaning of the tag, so you can select the QEMU binary by specifying in a meson.build file, and you can select the machine by simply calling the right function in a test. Now let's jump into it. So you've got a folder with .py test files. The first thing you need to tackle is how do you decide which files should be handled in your test framework. Avocado simply scanned all .py files in a folder and looked for tests in there, and then read this timeout variable from the files and used it to cancel the test after a while. In a new functional framework, we are doing it the Meson way. So you now specify the list of tests that you want to run and the timeouts in the meson.build file, which looks slightly like a little bit more work first, but it's simply the way Meson works. So most other test subsystems in QEMU are already doing it this way, and also if you want to compile a .c file, for example, you always add it to a Meson file. So that's the way to go. The nice thing about the Meson test runner is that it also allows you to specify a priority. So we can use the timeout settings now for setting the priority of the test. So the tests that likely run for the longest time, since they have a very high timeout value, they can now be scheduled to be run first. So they hopefully finish in time together with the short tests that are started later, since they have a shorter timeout value. It's especially useful if you have a lot of CPUs in your host system and you run everything in parallel. Now we specified the .py files, but as you've seen earlier, there are still these subtests in each file. So you need a way to discover these subtest methods and a way to run them. Fortunately, this is very basic in a basic thing in Python. And Avocado simply copied that concept. So in Python, there's the standard unit test class, which allows you to discover such methods that start with the test underscore prefix. And it also runs these methods for you. So by deriving our, do I have a mouse pointer here? Yeah. By deriving our QEMU system test class from that unit test class, we get this functionality basically for free. And the nice thing about that one is also that you can run your tests standalone by simply adding these two lines that I showed here on the slide, by simply calling the main function of the QEMU system test class, which in turn calls the main function from the unit test class. So that was already quite a big step to solve all the problems. Now, the next thing is that the test runner, by default, only treats each file as one big test. But if you have a lot of subtests in each file, it would be nice if you see the test runner executing each subtest step by step, just to get a nicer display of the progress. And there's a solution for this. There's the TAP protocol, the test anything protocol, which allows a test to tell the test runner which subtest is currently running. And indeed, there are a bunch of implementations for this for Python already. Like, I think if you Google for it, I think the most famous one is the TAPI module. And I tried a bunch of them, but everyone had problems. So I was close to giving up already. But finally, I still found the module called PycoTab, which is very small and does a very nice job. So this is working very well. So long story short, if you want to do Python-based testing with the meson test runner, give it a try with PycoTab. It works very well. Okay, back to you.
Thanks. So one of the core requirements for functional testing is that we're running real VM workloads. So we need various large file assets, whether they're kernels, RAM disks, disk images, or firmware. And we don't want to be downloading those test assets on the fly, because the download servers may be slow and that will cause the tests to time out. So we have a caching mechanism built into the test framework, and we have arranged so that the assets are all proactively cached before the tests actually run, so that the download and caching happens outside of the meson timeouts, which is quite important. And this basically mirrors what we already had available with Avocado in terms of caching, which was important because we didn't want to have a regression in this respect. The way this works when you're writing a test is that you have to declare an instance of the asset class at the test class level, and then we have a bit of logic that looks for all of the asset variables with a given name prefix and downloads and caches those files. You can, if you run the functional tests via the make check functional command, it will trigger the pre-caching automatically. But you can also trigger the pre-caching manually just by setting that environment variable listed there before running the test binary. Now, things aren't always foolproof with downloading assets. There's plenty of occasions in which the remote server is temporarily dead, or the network is unreachable, or any number of problems we encounter all the time. So when a thing isn't cached locally and we need to download it, if the download fails, then we automatically skip the tests that need those assets so that we don't break the entire test harness just because of a transient error. The only exception to this is if you get a 404 error code when downloading the asset, because we think that is probably an indication that the asset has gone away permanently, so we treat 404 errors as a fatal error. In some circumstances, we can download assets in parallel, so we also have some locking around our local cache so that we keep it consistent even when we have parallel downloads. Going on to file management, when you're writing tests, there's a variety of files you probably need to make use of. Some of the files can be things that are stored in the Git source tree. Others are things that we download on the fly, like the assets, or there can be files we need to create. We've got various helper methods for dealing with these files in a consistent manner. So, for example, a scratch file is something that's created in the build directory and gets automatically deleted when the test runs, so that we don't leave stale files around that could trip up the subsequent runs of the test suite. If you ask for a log file, it'll put it in a certain location so that the log file gets uploaded as an artifact in the GitLab CI runner so that you can actually debug your tests in CI when they fail. And we've got a handful of other helper methods for dealing with certain types of file. And you just pass in the relative path to the file you want, and it'll return you a fully qualified path that you can use for accessing those resources. Now, many of the files that you're dealing with are not necessarily plain files that you can use straight away. Quite a lot of the assets that we download will be compressed in a wide variety of compression formats. Other assets are hidden inside archives, whether they're zip files or tarballs. So we often have a need to extract files from archives and uncompress them. And because there are so many different archive formats and compression formats, there's lots of different Python APIs for dealing with each different format, which is kind of tedious. So we provided a couple of helper methods that can handle any of the common archive formats or any of the common compression formats with a common API, just to make it easier to deal with these files in tests. And the format of the archives or the format of the compression is generally guessed from the file extension in the URL, but some of the URLs don't have file extensions, so you can actually pass in a format argument to say which format to decompress or extract with. We mentioned decorators earlier. Decorators are heavily used in Python testing frameworks as a way to control what tests run under what circumstance. In the ideal world, all the tests would be able to run every time, but the ideal world rarely exists. So there's often a need to selectively skip running of certain tests so you don't create an unnecessary failure of the test harness. So to try and make this easier and work in a more standardized way, we provide various decorator functions that you can annotate the test methods with. There's a list of all of them up there. I'm not going to run through them all, but just some examples. If there's a Python module that's not installed, you can automatically skip the test. If the test relies on some external binaries from the operating system, we can skip the test, and a variety of other things there. And there's more being added all the time as people come up with new scenarios. For example, yesterday someone was proposing a test which required the use of sudo, and obviously we can't assume that the environment the test suite is running under has access to passwordless sudo, so we want a decorator so that we can skip those tests which require privileges if we don't have sudo access. So now I'm going to run through a quick example of what a new Python functional test looks like. You'll notice it's basically very similar to what the old Avocado test looked like. It's just a slightly shorter, and that's mainly thanks to the helper APIs for dealing with compressed files and archives. So one of the machine type the test assumes runs. So in this case, we use a method just to set the machine type. This is an example of the new asset handling. You can see the asset variable declared at the class level. It has to have the name prefix asset all in uppercase for the pre-caching logic to identify it and download the files. And then when it comes to use the asset, you can you can pass the asset directly to the archive extract method, and it'll just do the right thing to locate the cached asset and then extract it and so on. And when extracting the files, if you don't need the entire contents of the zip file, you can tell it just to pull out one individual file from the archive, so you're not wasting time and disk space. The decorators we mentioned on the previous slide, this is an example of a decorator for an unreliable test. I mean, we'd like all of our tests to be perfectly reliable, but every now and then we come across problems, and it gets very annoying when you're trying to get pull requests merged if tests are non-deterministically failing. So when we identify an unreliable test, we don't want to spend time debugging that straight away. We want to just mark that as a flaky test, file a GitLab bug, and tag the test with that bug URL, so then we can get the CI working again quickly and worry about debugging the unreliable test at a later date when we're not under time pressure. Sorry, just at the very bottom there, that's those two lines we put at the bottom of every test file. That makes it possible to run the Python test files directly without having the meson test runner in the middle of your execution, which makes it easier to debug some kinds of failures. Pass back to Thomas.
Right. So for running a test without the meson test runner in between, you basically have to do something like this here. So you've got to set the Python path to some folders in the source directory. Then you've got to set the QEMU test QEMU binary environment variable to the right target binary. So this is normally what the meson test runner is doing for you. And then you can run your test directly, preferably by using the Python binary from your virtual Python environment that QEMU sets up for you. And this is really useful, for example, if you're doing debugging for doing strace on your test run to see what I/O controls and system calls are done there. And yeah, getting information out of CI tests is always a challenge. It was also especially a challenge for the Avocado-based test, where a lot of people that did it for the first time were struggling to find the right log files where the information has been written to. So for the new functional framework, we tried to keep it simple. Hopefully we did. Hopefully you will agree. So the log files are now simply placed into the build directory like every other thing that is generated during compilation of QEMU. And you can find in the build directory in the test/functional/target name/name of the subtest folder. And there are always three log files. There's a base log that contains simply the logging output of your Python test class. There's a console log that contains the output of the serial console of the guest. And there's a default log file that simply contains the standard out and standard error from QEMU. And of course, if the test has some other specific files that it generates, you can also find them there. And we also upload these files as artifacts in the GitLab CI. So if your test is only failing in GitLab, you can grab the artifacts from the GitLab page. Now, if you don't want to run a test standalone, just run it via the meson test runner. The official way to do this is to type make check-functional, since we still wrap all meson stuff via make in QEMU. That's simply a convention by now. You can also run make check-functional and then a target name, ppc s390 x86_64. If you only want to run the functional test for a certain target. Now, during development, the normal QEMU developer runs make check at the end of the development to check whether there are any regressions or not, since make check runs most of the other test suites. We did not want to add all the functional tests to this test invocation simply because the functional tests download assets from the internet and we don't know whether the developer is on a proper internet connection or not. It could be metered, it could be slow, so that would have been a bad experience, I think. On the other hand, there are some functional tests that don't need any assets at all, so it would be great if we could run these tests during make check. So we needed a way to distinguish them. And the solution we came up with is that in QEMU, in the other QEMU test suites, there are different speed classes. There are the quick tests, the slow tests, and the row tests. And only the quick tests get run by default if you just type make check. So the idea was here to add tests, the functional tests that don't need an asset to this quick class, and all other tests are added to the row class instead. Long story short again, since the row class is a superset of the quick class, there's still a way that you can run almost all tests at once in parallel, and that's by doing something like make, then dash j, number of your processors, and check, and then speed equals the row. Then you're pretty good in testing if your code changes survive that one. So this is a screenshot how it looks like in action. I don't want to do a live demo here since it takes quite a time to run through the tests, but you can simply do it by after you compile QEMU, simply run make check functional or with a trick with using the row class. And so we are getting to the end. Let's talk about future plans. So things we still want to tackle is that we have to improve the download cache. Currently the cache is only growing, but sometimes tests get changed, they use different assets, or tests get removed, but the asset still stays there in the cache. So we need some logic somewhere that evicts old, stale assets from the cache after a while. Apart from that, there's still some stuff we have to do for error handling. For example, if QEMU crashes, often the tests are currently timing out instead of canceling directly, so there needs to be more detection for QEMU crashes. And then there are the various Python linters, MyPy, Flake 8, and so on. We should maybe enforce them to get better coding style. And of course, always add more tests for uncovered areas. So we've got a nice page in the QEMU wiki that lists all machines and which one already have a test and which one don't have a test yet. If you know that one of the uncovered machines, that there's an asset available somewhere in the internet that we could use for a test, please get in touch, or even better, try to write a functional test directly. So that's pretty much it. I hope this is fine for you. Thanks for your attention, and yeah, we're a little bit short in time, maybe 1 or 2 questions. If not, grab us in the hallway afterwards. Do we have them?
Do you want to take that mic to him?
Test. Okay. So my understanding is this is essentially conceived as a replacement for Avocado. So you looked a lot to check all the boxes that did, and maybe make an improvement or two along the way. Yeah?
Yes.
That's like the rough idea.
It's a replacement for Avocado that
Right.
tackles all the same
Yeah.
things that we had before.
So a thing, and maybe I'm just odd, but a thing that always struck me as a little bit odd with this system is that we download all these assets from somewhere. And so if you're a large company, you can make these images and you can publish them and you can make them available for the longer term. But if I'm not, or if my organization is particularly strange in these ways, then it can be difficult for me to add a test if I rely on an image to have a certain bit of functionality that none of the existing images do. And I mean, if nothing else, we also have probably quite a few images made. So a thing that I was wondering, do you have So I have a tool which I wrote, and one way that I decided to go around this is okay to say I want enough code to basically be able to spawn QEMU with some build arguments, and then take a cloud init based image, and then take some cloud init scripts and other assets and run that, and then out comes a built image, right? That's maybe not perfect, but it solves for a few distributions, and you can do quite a lot with that. Have you got any sort of ideas like that, so that I could just commit the assets to the QEMU project, and then if my test is run, we can build that image if it's needing to be built? Like,
we don't want the QEMU Git repository to get very large and full of assets, so we definitely don't want them in QEMU.git. And as a more general legal problem, we don't want to be hosting built assets, because then we become responsible for GPL compliance or other license compliance. So we'd much rather someone who, if someone's already publishing images we can use, we'd much rather let them worry about all the license compliance stuff and not host stuff on the QEMU project ourselves.
right. But in the case of building, for example, a cloud init-based image, you're holding a script, the cloud init YAML file, essentially with some instructions to say boot Fedora, DNF install, blah, 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 blah. And you're pointing to the base cloud init image for, say, Fedora core or Fedora these days. So you're not really hosting anything. You're hosting the baking recipe, and then the...
Well, if it's just a recipe, then yeah. I mean, the old Avocado system had some cloud init-based tests, but we eliminated them during the conversion. But there's scope for thinking about cloud init for further tests in the future.
Okay, yeah, that was it. Thanks.
We should probably hand over to the next speaker so that we don't run too far over. So come and get us in the hallway if you'll have more questions. Thank you.
Thank you.